everyone. Today we're going to start talking about electrostatics. Essentially, electrical phenomena without any dynamics, charges that are not moving. And we're going to start with Coulombs law and the electrical field. So, as we said in the introduction to this course, people from really olden times were aware of electrical phenomena existing in nature, and they were aware of something called charge, in the sense that they were aware that you could take a rubber or a glass material and you can rub it, and it will gain a property. What they thought at the time was some sort of electrical fluid. At those times, similar to what they thought, people thought of heat. Initially, people thought of heat as some fluid, the caloric. That's why we call heat energy calories, or we use calories to measure heat energy. People used to think that there was a fluid in everything that was responsible for heat. So they call that the caloric. And it made sense to them that, hey, if two objects touch, the caloric will flow from one object to another. So in a similar manner, people thought of electrical phenomena as being some liquid that is contained in matter that moves between different objects. And when it's displaced in a matter so that there's no equilibrium, you get objects that attract each other or repel each other. And this sort of electrical property, they called it charge. So charge is essentially a property that matter has. So if you have a piece of matter, let's say a cube of matter, it could have a mass, essentially its inertia, its resistance to motion, and it could have a charge. You could rub it, and it could obtain some charge, right? It could spark. It could attract another object with the charge. Now the question is, for this to be a quantitative science, is how do you measure this charge? How do we this concept that we assumed matter to have, how do we measure it, right? So that's when you want to do, and that's the problem that also people were faced with when dealing with heat. Okay, I can describe heat qualitatively. I can say heat is this, you touch it, you feel that it's hot. But to make it a science, you have to figure out, okay, how do I measure it? How do I determine exactly how hot an object is, or exactly how cold an object is? How can I plug a number on it? So the way people approach that is by tying it to force. Okay, I have two objects, and I can rub them, and they can, I don't know, accumulate some positive fluid here, and I can accumulate some positive fluid here, electrical fluid. I'm using the understanding of people at the time, like hundreds of years ago, 200, 300 years ago, right? How can I quantify how much charge did I add to this object? The best way is to tie it to mechanics. And at the time, people understood mechanics in terms of force. So you can, okay, how much force, like if I take this object, let's say this is a standard object. I rubbed it with a cloth 50 times. I take this object, another object, and I rub it like 10 times. How much force does this object exert on that object, right? So I can use this sort of thing to because I know how to measure force, I know how to measure mass by weight. So I can use this sort of thing to measure charge, some sort of way to measure how much charge there is in a piece of matter. As you can see, it's a matter of perspective, right? So it's a matter of your unit system, right? So there are many ways. Charge is an inherent property of matter. There are many ways to measure it depending on what system we use to measure charge, to quantify charge. In this course, we will use what's called the SI system. SI system stands for System International. It's a French system. And we don't really have to use it, but it's really common in engineering. If you go and study the subject from another perspective, let's say you are in a physics course, you would be using something called the Gaussian system, which measures charge with different sort of units. But we're going to use the SI system, and the SI system has units, mechanical units of kilogram for weight. It's the kilogram is some I don't know, some iron mass. I forget what the material is. Some kind of material, and it started as some kind of block of something under a bell jar in a lab in France somewhere, in Paris somewhere. And then it evolved into something else. I don't know what it evolved to. And then there's the meter, and then the second. The meter started again as some 2 H's on a rod. And now we use the speed of light to define the meter and seconds. Right, so those are the mechanical units. And then finally, the ampere is the basic unit of electromagnetism in the SI system. You can derive everything else. You can derive units for magnetic charge, electrical currents, charges, everything using the amp. Amp is a unit of electrical current. And the reason the ampere was introduced as the base unit in the SI system is because it's really easy to measure. Because it's very easy. I mean, once people invented batteries, it became very easy to get current to flow through wires. And people discovered pretty quickly in the 1800s that if you have 2 wires with current passing through them that are parallel wires, there's going to be a force F between the wires. The wires are going to expel each other. And if the currents in the opposite directions, the wires are going to attract each other. And you can easily measure this force. So it's a kind of force that's easy to measure, much easier than measuring the force between two-point charges, right? So using defining it in certain, you can define the ampere in a certain way. You can say, if I have 2 wires that are 1 meter in length, and then I add a certain amount of voltage, batteries, let's say, because you can design a voltaic pile with a certain amount of plates. So I add a certain amount of electrical potential, a big enough battery, a standard battery, to each wire. And then I have a standard current passing, and then I measured the force. If the force is 1 Newton, then this current is 1 amp. Okay, so this is a easy way to kind of define a unit for current. Once you have a unit for current is just the flow of charge. It's how much charge is flowing per second. So what is charge then? Charge is amp per second. Charge then, your unit of charge is this flow of current, this one amp per second. That's the charge. If you wait 1 second, with 1 amp of current, a certain amount of charge is going to flow. So 1 amp per 1 second is the basic unit for charge. This basic unit in the SI system is called the Coulomb, C. So this would be the basic unit of charge, and the SI system is derived. It's a derived unit. That's what I'm trying to arrive at. The unit for charge in the SI system is a derived unit. The basic defined unit is the amp. And it's defined based on a standard 2 wires with a standard current passing through them and measuring the standard force between them and making sure it's 1 Newton. Okay, that's how you define an amp. You should always in your system define a base unit, and then other units in the system are derived from this base unit. In the SI system, all you need is the kilogram, the meter, the second, and now the ampere. And that now you can have units. Everything else is derived from those 4. Now you have a complete set of units that you can use to obtain all the derived units for all mechanical and electromagnetic phenomena. So now that's charge. So this is charge, property of matter, and now we have a unit to measure it with. We have a method. Someone tells you, hey, this ball has 5 coulombs on it. you should know that there is a precise way to measure that, and it's a very repeatable way. So like a lab here or a lab in Switzerland is gonna, the 5 Coulomb here and 5 Coulombs in Switzerland is gonna be exactly the same charge. The unit is defined well enough that we can measure charge accurately through mechanical force, essentially, between wires. Okay, so this is charge, right? But I'm talking now about point charges. So I'm talking about, let's say, a box. I'm talking about the total charge of an object. How is charge distributed in matter? So charge exists in matter, right? But charge can be distributed in matter in different ways, right? So for example, this table. Let's say this table has a charge on it. How is the charge distributed? Is it distributed like across all the matter of the table? Is it only distributed on the surface of the table? Is it distributed on the edges of the table? So how charge is smeared leads to different kinds of charge distributions, right? So charge distributions can come in different 3 main flavors. They could come in a line charge density. It has units of Coulomb per meter, essentially a thin wire. Imagine a thin wire that is essentially has no diameter, or you can approximately say that diameter is 0. You can imagine that charge to be stretched along the wire. So you say per meter, every 1 meter has a certain amount of coulombs, let's say 5 coulombs. So the charge density in this case, line charge density, is 5 coulombs per meter. So you can describe the smearing of charge as if it is on an abstract line, right? We say abstract here because you don't have anything in the universe that has no width. I mean, even the electron has width, right? But this is mathematical. Mathematically, we can imagine a line with no width, with width 0, and we can imagine the charge distributed on this line. So we call this sort of distribution a line charge density. Of course, we could have a point charge. In this case, there is no distribution. Everything is concentrated in that point. It's really a matter of perspective. Like the electron might have a width. Like the electron has a width, right? But if we zoom out to our macro world, the electron might as well be a point charge. Same thing, if you have this line string with charge, if you zoom out a lot, let's say this string is some string on the table. If I zoom out to Jupiter, from Jupiter, this string might as well be a point charge. So it's all a matter of perspective. The mathematical model that you choose to describe how the charge is distributed is all a matter of your frame of reference. Sometimes it's good to approximate something as a point. Sometimes it's good, more appropriate, to approximate something as a line. If you, let's say, you have some line structure and you're really close to it, such that you cannot approximate it as a point accurately, so it's better to approximate it as a line. The other sort of mathematical charge distribution that you could consider, of course, is surface. You're seeing where that's going. Charge density. In this case, the charge is distributed over a surface. So the units would be Coulomb per meter squared. So this could be a sheet. Let's say a dryer sheet, something with a surface. You cannot accurately approximate it as a point if you're close enough to it. And also you cannot approximate it as a thread. It's something that has a surface. So the best way to mathematically represent the smearing of the charge on this surface is using a surface charge density. It has different units. It's Coulomb per meter square. And finally, you might have an object that is not a surface nor a point. It's a volume. So you could have a volume charge density. In this case, the units are Coulomb per meter cubed. Now, the thing about those charge densities, those can be either uniform, meaning that the charge is distributed equally everywhere in the object, or they could be non-uniform. Right? You might have, a ball where the charge is concentrated in the center. and then little charges on the surface, right? For the electron, for example, we assume that the charge, historically people assume that the charge distribution is pretty much uniform. People assume that the electron is a ball with a uniform charge distribution. Of course, people discovered later that the electron is not a classical object. You cannot really describe it in any coherent way using classical theory, but that's another story. Right, so this is charge distribution or charge density, which is we're going to deal with a lot, which is essentially charge smeared over a line or a surface or a volume. So this way of describing charge density, you notice that charge density, whether rho L, we typically use rho to describe charge density, or rho S or rho V. Those are one kind of field. Remember, we studied fields. So this is one kind of field in the theory. This is a scalar field. This is a number at every point in space, and every point on the line, and every point on the surface, and every point on the volume. It's a number. It has no vector qualities to it. So this is the first field we introduce into the theory, which is a scalar field. In mechanics, a similar concept is mass density. So mass density. You could have kilograms per meter, kilogram per meter square, or kilogram per meter cube. Mass could be same weights, either in a point, concentrated in a point, distributed on a line, smeared on a line, or distributed on a surface, or distributed over a volume. Different mathematical approximations of how mass is distributed in the objects that we're dealing with in a day-to-day life. Okay, so we can describe a charge density. The charge density can be uniform or non-uniform. How do we find the total charge? Let's say someone gives you an object and tells you, hey, this is its charge density. Well, if the charge density is uniform, the total charge is easy. Total charge is just the line density times the total length. For a surface object, so it's just the surface density times the total surface. For a volume object, an object that has a certain volume, is the volume density, charge density, times the total volume. Simple. What if the charge is non-uniform? If non-uniform, we have to integrate, of course. Yeah, the charge density is non-uniform, but at every small portion of the volume or the surface or the wire, we can consider the charge distribution uniform locally, and we can integrate. We can integrate and find the total charge. So let's do an example. Say someone tells you, hey, there is a uniform charge distribution. Right, but the total charge 10 to the minus 19 coulombs. Someone tells you, hey, this is the total charge. 10, this is the total charge, right? But this total charge now is distributed uniformly over different objects. So let's say it's distributed over a wire of 1 meter length. So this wire is assumed to be, someone tells you at the beginning, this has no diameter. Assume it to be a mathematical wire, right? If the diameter is so small compared to the length, we can approximate the diameter to be 0, right? So what is the charge density? Rho L, the line charge density. Rho L. So it's just the total charge Q over the total length of the line, 1 meter. So it's 10 to the minus 19 coulomb per meter. Easy. What if someone comes back and tells you, oh, no. This actually wire has some appreciable diameter. Consider the diameter of the wire, right? Consider the diameter to be, so the wire is still 1 meter. And consider the diameter to be 10 millimeters. 10 millimeters is what? Is 10 to the power minus 3 meters, right? And assume that the charge is distributed only on the surface of the wire. There is no charge in the interior. And this is something that happens in conductors, by the way. The charge is distributed always on the surface of the conductor, because the charge kind of moves freely in the conductor, and it all settles on the surface. In this case, the charge density you're looking at is a surface charge density, because everything is concentrated on the surface. What is that surface charge density? Well, you have to take the total charge and divide it by the surface of this object, right? This object, by the way, continues on both sides. You're only looking at 1 meter of it. So the surface is going to be the diameter of the side circle of that cylinder, which is 2 pi d over 2. What's that? That's going to be pi d times the length times 1 meter. So it's going to be meter squared. So it's going to be 10 to the power minus 19 Coulomb per meter squared over pi times 10 to the power minus 3. If you do this calculation, this turns out to be 3.18 times 10 to the power minus 18 Coulomb per meter squared. And finally, assume this is kind of like not a metal wire. Assume this is some sort of material that's not conductive. So the charge is distributed over the volume of the material. In this case, you'll have a volume charge density, which is the total charge divided over the volume of this thing. What's the volume of this thing? It's the area of this side, which is pi d over 2 squared, pi r squared, right? Times 1 meter. So it's going to be meter squared times 1 meter, meter cubed. So if you do this calculation, it's going to be 1.27 times 10 to the power minus 15 Coulomb per meter cubed. Okay, so this is easy enough. What if we have a non-uniform charge density? Someone tells you, hey, assume the coordinate system is spherical, and I have some object that's a ball centered around the origin, and then the volume charge density is going to be some initial charge density times r Coulomb per meter cubed. Those brackets means the units, right? I'm describing the units. So this is a sort of charge distribution that increases with radius. So this is charge that is concentrated the further you go towards the surface of the ball. And assume this ball has a radius of r0. So at the center there is no charge distribution because r is 0. As you increase the radius, as you move towards the surface, R0, the charge distribution increases linearly. Okay? The question is, what is the total charge? This is a sort of problem where we cannot find the total charge unless we integrate, because the charge distribution is non-uniform. So we have to take the charge density and integrate it over a volume. So this is an example of taking a scalar field and integrating it over a volume, a non-uniform scalar field, and integrating it over a volume. Luckily, we know how to do that because we know what depending on the coordinate system, we know what the volume differential element is. Remember, we studied that. So we know that the volume differential element is just r squared sine theta dr d theta d phi. That's one infinitesimal volume. That's one infinitesimal volume in 3D space in spherical coordinates. And then what we're integrating is r, rho naught r, right? This is the charge distribution, and this is integrated over the volume. So to cover the whole volume, r needs to go from 0 to r0. Theta needs to go from 0 to pi. You know, according to the coordinate system, we go from 0 to pi. This is z, right? To cover the whole sphere. And then phi goes from 0 to 2 pi. So this is how I integrate over the whole sphere. And it's just now a matter of integration. I can now take the constants out, r naught, I have from 0 to 2 pi, from 0 to pi. I integrate r cubed with respect to dr. R cubed is going to be r4 over 4. That is integrated from 0 to r0. But then I have sine theta, d theta, d phi. Right? So now I can calculate this. This is going to be r0 to the power 4. So I can over 4. That's it. That's what's going to be. So I can erase this. So this is going to be, I take it out. It's a constant. r0 to the power 4 over 4. That's what it's going to be. And now I need to integrate sine theta. What's the integration of sine theta with the d theta? That's minus cosine theta, right? Minus cosine, when you differentiate it, you get a sine. So this goes, the limits of integration are 0 to pi d phi. What is this? What's minus cosine pi? Cosine pi is minus 1, right? So minus 1 times minus is plus, plus 1. Minus, minus, plus cosine 0 is 1. So this whole thing really becomes 2. 2 cancels with the 4, and I end up with 2 here. Integration of d phi, there's nothing here now. It's a constant, 1. This is just 2 pi. 2 cancel with 2, and we end up that the total charge is going to be pi r naught, rho naught r naught to the power 4. It's proportional to the 4th order of the radius. Meaning if you double the radius, let's say you double the radius, according to the charge distribution, which is just linear, if you double the radius, 2 to the power 4, what's 2 to the power 4? 16. So if you double the radius, you have 16 times more charge, essentially. Okay. So this is all an exercise in integration. You might have different charge distributions, and it's a really just a mathematical exercise. What is the total charge? It's just a matter of integration. Coulombs law. So now we know how to quantify charge. And we said historically in the SI system, charge was quantified based on the ampere unit, right? Regardless of what the history is. Now we know we have a way for someone tells you, hey, this is 1 coulomb of charge, you can trust him that this is 1 coulomb of charge. You know how to measure charge. The question is, how do we tie the charge to the force between charges? So charge, the point of objects having a charge is that if if we say objects have a temperature and then it does nothing. Temperature is some mysterious, invisible quality that has no effect on the real world. Nobody cares. But charge has effect on the real world because charged objects attract and repel each other. So the question is, if I have 2-point charges, this is the simplest, forget about any structure. This is the simplest kind of object you can study, a point. Like the planets, planet Earth, with all its complications, and cows and deer and animals and rivers and mountains, with respect to the sun, Mars, all the planets, is a point. Right? Everything is so far apart that we can consider the whole planets to be points. And then we can study the gravitational force between them. Same thing, what's the simplest thing we can consider? The simplest thing we can consider is that we are so far away, the objects are so compressed that they are mathematically points. Okay, then how do they interact with each other? It turns out a guy called Coulomb discovered that they exert a force between each other. So they either attract each other or they repel each other. And furthermore, this was after, by the way, the establishment of gravitational theory, Newton's gravitational theory. He discovered that the force between them is exactly like gravity. in the sense that the force is proportional to the inverse square law. So if you know the distance between the two objects that can be approximated as points, if you know the distance between them, the force between them is going to be proportional to the inverse square. Meaning if you double the distance between them, the force between them is a quarter. If the distance between them is 10 times, the force between them is now 1/100th the original force. So the force obeys that property. And Coulomb kind of described it mathematically. Well, he did not describe it this way. Vector calculus did not exist at his time. But now we can describe it using vector calculus as follows. We can describe it as r hat, where r hat is essentially, so if I have q1, q2, r hat is essentially a unit vector between q1 and q2. This is not the basis vector from spherical coordinates. This is just a basis vector, not a basis vector. This is a unit vector, meaning a vector with magnitude 1 that starts at q1 and points to q2. That's all it is, right? And then the force is going to be some proportionality constant, q1, q2 over r squared. R is the distance between the two charges. Newton. This is exactly similar, analogous to the Newtonian force of gravity. It has the same form. The constants are different, though. The proportionality constant is different. The magnitude of that force, of course, is just k q1 q2 over r squared. Right? It's a simple law. It's the inverse, what's called the inverse squared law. It was quite a surprise at the time that the inverse squared law also applied to electrostatics, right, and gravity. For historical reasons, we don't use K. For historical reasons, because of how the subject developed, the constant is different than K. The constant, we define the constant as follows: K equals 1 over 4 pi epsilon. So we introduce a new concept called epsilon. Why don't we just stick with K? Well, Coulomb's original papers used K. But the reason is that some guy called Gauss came in and used something called Gauss's law, and which we will study, and derived the equation Coulomb's law in a different way. So he introduced something called epsilon. But it's the same. It's like you're substituting one constant with another constant. So for historical reasons, when people introduced Coulomb's law, they introduced it using this different constant. It's easy to switch between the two. I mean, if you have epsilon, you can get K using this way. If you have K, you can get epsilon just by noting that epsilon equals 1 over 4 pi K. It's just a constant relationship between them. Epsilon is something called the permittivity, or what's called the dielectric constant. Right now, just take it as being a constant. It's gonna later in the course, it's gonna make sense why it's called like that. Why it's called that. By the way, K. What are the units of K? The units of K are what? K has to cancel out the units of charge and distance squared and give me unit of force. So K has to give me Newton at the end, because force is measured in units of Newton. What is Newton, by the way? From F equals ma. Newton is just mass, kilogram, and acceleration is meter per second squared. Remember how we said every derived unit goes back to the fundamental SI units? So Newton is a derived unit. I can always represent it in terms of the fundamental units, which are kilograms, meters, and seconds. Right? And then Coulomb comes in, which is the derived unit, which can be represented as amp seconds. Okay, so what are the units of K? Well, K needs to generate newtons at the end, and it needs to cancel out the Coulomb and the distance. So it needs to be meter squared, right, because it needs to cancel out the units of the R, over Coulomb squared. This is the units of K. What is the unit of epsilon? Well, it's just the inverse of this, right? So epsilon, because it's in the inverse position. So the unit of epsilon is going to be Coulomb squared over Newton meter squared, right? And again, because of the way the subject is developed, we can write this as Coulomb squared over Newton dot meter over meter, right? This thing, for reasons that we will discover later, bear with me, is called the farad. So the classical way of introducing epsilon is by giving it the unit of farad per meter. What is the farad really? Don't worry about it at this point. Consider the farad just to be a collection of different units. Consider the farad to be Coulomb over Newton times meter, essentially. Coulomb squared over Newton times meter. Someone tells you, okay, that's fine. This strange unit called the farad, you define it this way. Can you write it in terms of fundamental SI units? Those are all derived units. Well, we know that Coulomb is amp per second, right? Times seconds. So it's going to be amp squared, second squared. We know that Newton is F equals MA. So it's going to be kilogram meter per second squared. And then I have meter. So times second squared is going to be second to the power 4, right? And this is meter squared. So in terms of fundamental SI units, the farad is really amp squared, second to the power 4 over kilograms times meter squared. You should be able to go back to the fundamental units of your system, right? Anyway, this is all for historical reasons. Don't worry about what the farad means right now. It's just a collection of units that we collect together and call it a certain name, okay? This constant, by the way, K, whether it's K or epsilon, can be found empirically, experimentally. I could bring in 2 coulombs, put them 1 meter away from each other, measure the force, and depending on what I measure in the lab, I determine what K is. And in this case, we determine what epsilon is. It turns out that if we're in a vacuum or air, which is really close to a vacuum, epsilon is something called epsilon naught. So this is for air, which is really close to a vacuum. So it turns out this constant turned out to be 8.854 times 10 to the power minus 12 farad per meter. Okay. So the form, in summary, the form of Coulomb's law, the magnitude of F is going to be Q1, Q2. Instead of K, I put 1 over 4 pi epsilon naught for vacuum, R squared, Newton. So let's formalize. So formalize so that we have a really standard way of doing calculation. The way we formalize how we calculate using Coulomb's law is as follows. As always, when you do a calculation, you need to have a coordinate system. Coordinate system has an origin, O. Right? And then you have your 2 charges, Q1 and Q2. Someone's texting me. A scalar field is called rho. It's rho. This is the charge density. Okay. Right. So there's the way to formalize describing the force between 2 point charges is to introduce what's called the position vector. So I could consider a vector going from the origin to Q1, call this R1. This is a vector that represents the position of Q1. And then I can have a vector that goes from the origin to Q2. This is going to be a position vector that represents the position of Q2. Notice that R1 and R2 are not unique for Q1 and Q2. Why? Because they're going to depend on the coordinate system. If I have a different coordinate system with a different origin, R1 and R2 are going to be different. However, the displacement R1 minus R2 and R2 minus R1, which should lie on this line between the 2-point charges, is not going to be dependent on the coordinate system. Because of this, in some treatments, you would see people say that the position vector is not a real vector. Right? That the displacement vector is the real vector. The reason people say that is because people like to think of vectors as objects that do not change based on the coordinate system. Position vectors are those weird kind of vectors. They're not physical vectors. They're imaginary vectors. There's something to just point the position to somewhere. They're not like a wind field, vector field, you know, where it's really a physical phenomenon. They're like something imaginary because we imagine the coordinate system. We imagine something pointing to where something is living in the space. So because of that, many treatments, they don't consider them a real vector, but that's kind of like a semantic argument. So if you hear that argument, remember that that's the point, is that R1, what R1 and R2 really is as a directed line varies depending on where your origin is. However, R1 minus R2 is going to be the same because the distance between Q1 and Q2 is going to be the same regardless of what your coordinate system is. So using this, we can formalize the vector between 1 and 2. What R1, 2 means here is the vector starting at 1 and ending at 2. And we can write that. So how do I represent the vector starting at 1 and ending at 2? R1, 2. This is clearly R2 minus R1. So minus R1, you flip R1, and the vector goes from the tail to the head, right? Then we can define R21, which is the vector that starts at 2, it ends at 1, the opposite vector. Starts at 2, it ends at 1. And this is clearly R1 minus R2. Oh, don't I have charge? Oh, this is disconnected, sorry. Okay. So when you see R1, R2, think vector starting at 1, ending at 2. How do I write that? I write that as R2 minus R1, just from examining. R21 is vector starting at 2, ending at 1. So I have to flip to go from tail to head. I have to flip R2. So R2 has to have the minus sign. This is R1 minus R2. Furthermore, we can define R12 hat and R21 hat. Those are just the normalized version of those vectors. This is just R2 minus R1 divided by magnitude R2 minus R1. It's the same vector as R12, but with a magnitude of 1. It's the normalized version. And then this is R1, because sometimes we want to only capture the direction. We don't need to capture the distance, right? R1 minus R2 over magnitude R1 minus R2. Okay, so this now allows us to write Coulomb's law in this form. So we could write the force F12. What do we mean of F12? We mean that the force Q1 exerts on Q2. This is what we mean when we write F12. So if I have Q1, Q2, this is the force Q1 exerts on Q2. This is F12. So F1 reaches out to Q2 and exerts a force on it. To calculate this F12 is the same direction as R going from 1 to 2. This is R12 hat, right? So we write this as Q1, Q2, R12 hat, because it's the direction going from Q1 to Q2. And now we see that if Q1 and Q2 are the same sign, it's two positive charges or two negative charges, it becomes a repelling force. Q1 repels Q2. If they are opposite charges, we introduce a negative sign, so we flip the direction of F12 and it becomes an attractive force. So you can see now in this formalism, attraction and repulsion occurs naturally in the math itself. Over 4 pi epsilon naught R12 squared. When I write this without a vector notation, that means this is the magnitude. If you write R12 without the vector, that inherently means you're talking about the magnitude. So here R12 is just magnitude R12 of the vector, and then R12 hat is just R12 vector over magnitude R12 vector. Further, also, we can talk about the force 2 exerts on 1. Let's say we don't want to talk about the force Q1 exerts on Q2. We want to talk about the force Q2 exerts on Q1. So this force is going to be in this direction, F21. We always assume that the positive is the force pointing away from the distance between the two charges. That distance is going to be in the direction of R going from 2 to 1, so R21 hat. So I can write this as Q1, Q2, R21 hat over 4 pi epsilon naught R21 squared. I don't have to use the hat. I could have easily said F21, Q1, Q2. Instead of R21 hat, this is equivalent to R21 over R21 magnitude. So I have an extra R21 here. So this becomes 4 pi epsilon naught R21 cubed. So this is another way of writing Coulomb's law. Someone might say this, oh, is Coulomb's law inverse cubed? No, it's not. Because one of the R21 magnitudes is reserved for normalizing this R21, just to gain the direction. So it's not really an inverse cube, it's still an inverse squared. It's just in this formalism it looks cubed because one of the magnitudes is utilized to normalize this vector up here, to cancel its magnitude, so that we can only get the direction information. Of course, we can write everything in terms of R1 and R2. So I can say F12, this is the force 1 exerts on 2, so we need to take the direction. So Q1, Q2, we need to take the direction from 1 to 2. So this is going to be R2 minus R1. I could decide to write everything in terms of R1 and R2, divided by 4 pi epsilon naught R2 minus R1 magnitude cubed. I need one magnitude to normalize this, R2 minus R1, and I need the square to apply the inverse square law. So this is the third way of writing Coulomb's law, mathematically, and it's equivalent. So I can say also F21, this is the first 2 exerts on 1, Q1, Q2. So it's the direction from 2 to 1. So I need to invert 2. So it's going to be R1 minus R2 over 4 pi epsilon naught R1 minus R2 cubed. Let's see. Let's do an example. So I want to do a new example 3.3 from the textbook. To have time, we have 2 minutes. So we have 2 charges, Q1, Q2. They're located at points 1, 1, 0. I'm assuming this is Cartesian. Yeah, I think it makes sense that it's Cartesian. When they don't specify the coordinate system, assume it's Cartesian. 3, 2, 0. They should specify the coordinate system. I guess they assumed by default it's Cartesian. So calculate the force Q1 between Q1 and Q2 if Q1 equals 2 to the power 10 minus 9 Coulomb, and Q2 is 4 times 10 to the power minus 9 Coulomb. The first step you need to do here is write R1 and R2. What is R1 and R2? So R1, and this is, by the way, easy to do in Cartesian. The thing is with the position vector, it's kind of tricky to do in anything but Cartesian system, because in Cartesian system, the basis vectors are the same everywhere. If you want to do a position vector in another, perhaps we should do an example about that. We'll do an example about that later. But the position vectors, one other problem with them is really tricky to deal with when you have anything other than the Cartesian system. In the Cartesian system, I just can write R1 as 1 x hat plus 1 y hat, and there's no z. Z is 0. And then R2 is simply 3 x hat plus 2 y hat. That's it. This is the R1 and R2, and it will be the same everywhere in space. The problem with spherical and cylindrical is that those are not the same, x, y, and the basis vector is not the same at every point in space. So it's tricky. You write R1 and R2 in terms of which basis vectors. Is it the basis vector at the origin? But at the origin for spherical coordinates, there are no basis vectors. Because there are, at the origin exactly, it's a singularity because the r hat points everywhere. So it's mathematically tricky. You can write the coherent basis vectors at every point except the origin. But thankfully, this is Cartesian, so this is easy. And now we can apply Coulombs law. F1 exerted on 2 is just going to be R12 hat Q1 Q2 over 4 pi epsilon naught R12 squared. And then I can easily calculate R12. R12 hat is going to be the distance between 1 and 2, right? From 1 to 2. So it's going to be R2 minus R1 over R2 minus R1 squared. Okay, what's R2 minus R1? It's going to be 3x hat plus 2y hat minus R1 minus x hat minus y hat, right? What is this thing? This thing is going to be 3x hat minus x hat is going to be 2x hat, 2y hat minus y hat, plus y hat, right? Over the magnitude of this squared. What is the magnitude? The magnitude is square root squared. The square root goes away. It's going to be 2 squared, which is 4, plus 1 squared, which is 1. So it's going to be 5. So R12 hat is going to be 2 over 5 x hat plus 1 over 5 y hat. We now have this. And then R12 is just 5. We calculated it. Right? And then we plug everything into Coulombs law, and we get the force as a vector. Yeah. All right, let's stop here. And we're going to solve a little bit more problems, and then we're going to introduce the concept of the electrical field. Thank you, everyone, and I'll see you Wednesday. Thank you.